It's okay, Juan. Yeah.
Okay. Bienvenidos todos. Esta es la segunda sesión de nuestro seminario de categorías de la UNAM. El expositor en esta sesión es Joe Moeller, de la Universidad de California en Riverside, quien nos va a hablar de modelos de redes. Si alguno de ustedes tiene una pregunta durante la plática, por favor escríbanla en el chat. Nosotros podemos preguntar la pregunta por ustedes, y si quieren que les quitemos el silenciador, por favor levanten la mano y les podemos quitar el silenciador. También va a haber una sesión de preguntas al final de la plática y también vamos a leer preguntas del canal de YouTube. So welcome everyone. This is the second session of our category seminar at UNAM. The speaker of this session is Joe Moeller from the University of California at Riverside, who was nice enough to accept our invitation. The title of Joe's talk is Network Models. If you have any question during the talk, please write it in the chat and we will ask the question for you. If you wish to be unmuted, please raise your hand and we will unmute you. There will also be questions round at the end of the talk, and we will be reading questions from the YouTube channel. Yes, please, Joe. Thank you.
Thanks. Hi, so I'll share my screen. Right. So yes, my title is Network Models. That's the name of the paper that this talk is going to be about. And so this is joint work with John Baez and with John Foley and Blake Pollard. Right, so the motivation for this work was a program from DARPA called Cascade, which is a long acronym that some of those words are about. It's about complex network design. So complex network design, and the idea behind the program is that they wanted to write some software that will help with this scenario. You have maybe there's like some particular area of ocean, and there's a lot of boats in the water, and then some hurricane happens or some other natural disaster, and people are lost out in the ocean. And now you have to perform some search and rescue operation. So search and rescue. And you have at your disposal some kind of collection of boats and helicopters and people that can cover this area and search for these people that you have lost. So you can like place these helicopters or boats or what have you at different locations, and you can task them with searching certain regions. But since this is happening like during a natural disaster, it's possible that these vehicles can also be taken out by the disaster and also become people you have to save as well. And the area that they were tasked with searching now has to be redelegated to some other units that you have that are still functioning properly. So in this setup, you're going to have a lot of networks of various sorts that you're going to have to manage, and that's the main angle that this stuff is being approached from. That we have a lot of networks and a lot of different types of networks, and they're changing over time, and we want to manage those in some sort of principled compositional way. The main way that we want to think about these networks, right? So like there could be, I didn't draw any edges here, but there could be like edges between these things that represent some relationship that these vehicles have to each other, or maybe like communication pathways that are established. And so the way that we want to think about building up networks from small pieces is in this way. This part is sort of a choice of what way we can think about networks. So let's say here are the nodes in a network that you want to build up, and like here's a small piece, and here's a small piece. But now you want to talk about adding new edges to this. Then you could look at this area like locally and say, within this area, I'm going to have a little model of this piece of it, and I'm just going to add this edge here. And so like this belongs to this area right here, and maybe this area over here has its own piece that we're going to add more things. So let's say that I add like these connections here. And so if we take this and we try to add these connections to this network, the result will have these old connections and then also this new connection, and then these connections and the old ones that were there before. Right, so this is the way that we want to think about connecting smaller pieces into larger complex networks. But I only did this for simple graphs, right? These are just simple graphs, which are just one type of network that you might want to consider. But in really complex scenarios, you could imagine wanting lots of different types of networks involved here. So you could have you might want directed edges representing certain like one-way relationships between vehicles, or you could want like a set of colors assigned to the nodes of these graphs. You could want multiple edges if it's possible to have multiple connections of a certain type, or you could have colors on the edges to represent different types of connections. There's really a lot of different things that you could be wanting to do that have this same basic framework. And on top of that, you could also want to change your mind about exactly what types of networks you have running around. So let's see, what am I saying? I'm saying with this picture that this looks like the structure that we want to work with is an operad. But there's a lot of different types of networks that we could want here, and so there should be corresponding different sorts of operads that would correspond to each one, and we should be able to, we want some kind of framework that would allow us to change our mind about which operad we're working in, or to have relationships between these operads. So that's what I'm going to describe in this talk. That's what we did in this project. Is let's see. Here's a desiderata. Here's the things that we want out of this project, and that I'm going to describe. We want to have so for each type of network, an operad that looks like what I was describing before. But we also want a good definition for type of network. So that we could make this second point make sense. And then we also want not just to take types of networks and turn them into operads, but we want ways to specify types of networks. So this is what we want to obtain, and this is what I'll describe now. So let's see. So what were the basic ingredients? In the picture that I had before. So when I described network composition by taking pieces like this and then adding in pieces at certain parts. So here's what I'll claim are these basic ingredients. We have an overlay operation, which I'll call union. And what does that look like? Sorry, let me just finish this. So what I mean here is that if we have like a graph with 3 nodes and another graph with 3 nodes, then we want some operation that tells us how you can combine these to obtain another graph with 3 nodes. So that's what's happening sort of in this local portion. Another one is a notion of taking a disjoint union of some graphs. So I'm going to denote it with this square cup. And this is something that you can do to graphs that have different numbers of vertices. 1, 2, 3, 4. Right? That's what happens at sort of this level when we have all of these smaller pieces and we combine them into the big piece. Then there's a third one that might be less obvious from the picture that I drew, but permuting the nodes. Right, so if I have a graph on 3 vertices and I have some permutation of 3, then I want to be able to turn this graph into another one on the same number of nodes just by permuting those nodes. It should turn into a different graph. So right now I'm working up towards a good definition for type of network, and these are the 3 ingredients that we want a type of network to have in order to make this sort of picture make sense. And so let's start with permuting the nodes. Recall that if you have a group acting on a set, that the right way to think about this as a category theorist is that it's a functor from the group thought of as a one-object groupoid into the category of sets. So X is a set that assigns the unique object of G to this object X. Right. So in particular, if our group is So if G is the symmetric group on n letters, then we have a functor from the symmetric group thought of as a one-object groupoid into the category of sets. Often in combinatorics, you have some sort of object or like a type of object that you want to think about. So like graphs, for instance, that have like the family of these objects can be broken down into like a graded family based on the number of nodes that the structure is built on. And if it has these n nodes, then it's often possible to permute the nodes and end up with some other instance of this type of object. And so, let's see, so often in combinatorics, we have this, we have like we have a family of objects. And the symmetric group acts on each one of these by permuting these nodes or whatever the right word for those elements is in that context. And so that means that we can think of this as like a family of functors going from the symmetric group into set. Should have called this F. But we could also just group all these things together and say that this is like one big functor going from disjoint union, the co-product of all these categories, one object categories into set. And so that's precisely what we're going to start with. So so let S be the category where the objects are natural numbers, or you can think of them as the set containing that number of elements, but I'm not going to distinguish the number and the set from each other. And in particular, 0 is the empty set. And then morphisms are bijections. So I'll denote that usually with a sigma going from n to n. So this is the same thing as, well, it's a skeleton. So this is a skeleton of finite sets and bijections. And that is that's the maximal groupoid, the maximal subgroupoid of thin set, finite sets, and functions. So this is going to be the thing that represents a family of, well, the family of symmetric groups. A combinatorial species is going to be the thing I was describing on the previous page. It's a functor going from this category S into set. Right, so this was defined by Joyal in 1981, and it's precisely what I was describing on the previous page. You have a family of objects, a family of sets, each that are being acted on by the symmetric group. A lot of combinatorics can be captured with these objects, and this is the thing that we'll start off with, right? So this is here's an example of a species that we care about. So I'm going to call it SG for simple groups. I'm sorry, simple graphs. So SG is the functor from S to set, where SG of N is the set of simple graphs with node set N. So like the set that I was describing before as N is going to be the set of nodes, and Sn acts on SG of N by permuting the nodes. Right, so that takes care of the specification of the morphisms for this functor. This is going to be the main, or like motivating example to carry us through to the definition of what we're calling like a type of network. Right, so this captures permuting of nodes that we wanted to have in our definition, and so now we still have overlay and disjoint union to incorporate. So overlay. So overlay is something that you can only do to graphs that have the same number of nodes. So overlay only works on graphs with the same nodes. And so we can think of this as a map, a bunch of maps of this form. So we have SG of N. We have two simple graphs on the same node set, and this is a map that takes them and turns them into one. And so, in fact, this gives SG of N the structure of a monoid. The unit object is, the unit element is the graph on N nodes which has no edges of a monoid. And so in particular, we can change SG to now be a functor from S into the category of monoids. And the only thing I didn't mention is that the permutations do in fact turn out to be monoid homomorphisms with respect to this map. But that's true if you think about it. So now we're thinking about a functor from S into category of monoids, and this does like completely incorporate or describe overlay operation that we want. Before we can do disjoint union, we have to consider more things on this category S. So S has a symmetric monoidal structure. Which we call plus, but it's not co-Cartesian, but it looks exactly like plus, so it would be silly not to call it that. So N plus M is exactly what you think it is. So I would just write equals N plus M, so that's kind of silly, but is what you think. And then if you have two permutations, I can draw a picture of that. So if you have two permutations, it's going to look like So let's say this is sigma. And this is tau. Then the result is just setting them right next to each other. And so this is a permutation on 5. And the unit object is 0. Right. And so now that we have this monoidal structure, then we can think about the disjoint union operation. This is something that you can do to nodes of any size. They don't have to match each other. And it like adds the number of nodes. And so we can think of this as maps like this. To take a simple graph on M and a simple graph on N and turn it into a simple graph on M plus N. And this describes exactly the structure of a lax monoidal functor. So this gives the structure of a lax symmetric monoidal functor. Right, so this is relating the additive structure on S and the Cartesian structure on monoids. Sorry. Monoids Cartesian structure. So this is turning our functor into a lax monoidal functor, symmetric. And the unit lax structure here is going to be the graph with no nodes and no edges. So this is now carrying the data of the overlay operations in these monoids, the symmetric group action in that it's a functor from S, and the disjoint union operation is the lax structure for this functor. And so this is exactly what we're going to take to be our definition for a type of network. So here's the major definition. A network model is a lax symmetric monoidal functor of this form. We have so a functor, lax structure map, unit lax, and then from S plus 0 into monoids with Cartesian structure. And we also have maps between network models. So a map is a monoidal transformation, monoidal natural transformation. So you have these two network models. It's a monoidal natural transformation here. And the category of these network models, we're going to call it net mod. Right, so these are things that we are considering as capturing the sort of right combinatorial features that we want to say that a network has. So anything that has these features, we can think of it as a type of network. So this is what I'm counting as satisfying our first desired property, a reasonable definition for a type of network. From this, we want to build operads in a sort of systematic way. And we also want a way of cooking up examples of these things. So let me give a few examples of these first, though. So multigraphs. So let's see, examples. Multigraphs. So multigraph is just a graph. It's like a simple graph, but the modification you make is that you are now allowed to have multiple edges between a given pair of nodes. And if you have one of these and another one, say like this, then there's a reasonable way of overlaying these two, where we have, what, 4 here and 1 here and 1. I guess I didn't. I'll describe simple graphs more. Wait, I didn't describe yet the overlay operation. Okay, the disjoint union of multigraphs is exactly the same as with simple graphs. So if we have this, I'll make it easy on myself. Then we get this. Okay. I think it's worth looking at what happens with simple graphs in more detail. So I'll just describe the overlay operation, or I'll give an example of the overlay operation that demonstrates sort of the distinction between multigraphs and simple graphs. So in the case of multigraphs, when you have edges on the same pair of nodes, you just add them. Like it just, you can have both of them and it's fine. But with simple graphs, you're only allowed to have at most one edge between any pair of nodes. And so in this case, where you're sort of overloading this pair of nodes, the result is going to just still have exactly one edge here. So you can also have directed graphs, and I won't draw too much of that, but just here's a picture of a directed graph. And you can have directed multigraphs, and you can have colored edges. And so that's going to work very similar to so let's say that you have these two colors assigned. I'll skip the directions. If you have these two colors, and then you have switch, and you want to overlay this with something that has maybe just 3 reds, then it sort of does the natural thing where you have 4 reds, 1, 2, 3, 4, and 1 blue. Right, so I'm just sort of trying to demonstrate the range of things that do come up when we're thinking about specific applications of this. There's a lot of flexibility in this. You can also do partitions. There's a way to make partitions have all of this structure, and Petri nets can also satisfy these things, and hypergraphs. Sort of a lot of things that you could imagine look like networks can be given the structure to be one of these network models. A non-example of a thing that is reasonably called a network but doesn't satisfy this is non-example acyclic directed graphs. Right. So an acyclic graph is one that doesn't allow this scenario. So you have directions on your edges, but you can't have this. This is not allowed because it has a cycle, and that's precisely what you're trying to restrict. And so if you had two of these acyclic graphs, so like this is fine, and here's another one, then obviously if you take their overlay, then it gives you this, which is not allowed. And so the most obvious way of like trying to make acyclic directed graphs into an example, it doesn't work out. Okay, so let me give a construction for how to get many of these examples and many more. So let M be a monoid. Then define so a network model called gamma M. By saying that gamma M of n is the monoid M, take the product of itself, n choose 2 times, right? So what I'm saying here is that, here's the picture of it. If you have 3, for instance, then the monoid that I'm describing here is going to be that an element is going to be a graph that looks like a simple graph on 3, but where the edges are weighted by elements of the monoid. And then when you try to overlay with another one, you just do the monoid operation on the corresponding edges. So I guess I'll put N1, N2, N3, and then the result is you do the monoid operation. So M1, N1, M2, N2, M3, N3. And so this is a network model, and in particular, it gives a, let's say this gives a functor that goes from monoids into network models. And so this is one instance of satisfying our third desired piece of data, which is a way of cooking up network models quickly. And it's just you take any monoid and you construct the network model in this way. And I'll add that the main example here is that if you take M to be the Boolean monoid, so that's like true and false and or, then gamma M is precisely the simple graphs network model. Because here you have like 0 and 1 as possible edges, and it's like there is an edge or there is not. And then when you overlay them, there's a 0 or 1, then that's 1. So if there's, yeah. Okay. Want to get to the construction of the operad before the time runs out. So let's see, constructing the operad. It's the second point in the desired data. So there's 2 steps in constructing our operad. So this is actually going to be a functor which goes from network models to operads, and it passes through symmetric monoidal categories first. So the first one I'll call integral because it involves the growth and deconstruction, and then the second step I'll just call underlying. So let me describe these. So first, let's see, I'll describe the growth and deconstruction. So the growth and deconstruction takes this as the input, functors going from some category into cat. And then we construct a category called integral of f, which has the objects being pairs, where you take an object of C and then an object in the category that little c is assigned to. So C in C and X in F of C. And the morphisms are going to be F comma G, going from CX to DY, where F is just a map from C to D in C, and G is a map from F of X to Y. This is happening in F of D. And composition rule that I'll skip for now. I don't want to spend too much time just talking about the growth and deconstruction itself. But I'll give an abbreviated version of my result with Christina Vasilikopoulou, which is that if F is a lax symmetric monoidal functor from some category into cat, its Cartesian structure, then integral of f can be given SMC structure by tensor the objects by taking, let's see, CX, and I call it tensor sub phi, with dy is given by C tensor D, and then phi of X and Y. So the lax structure map with its component at C and D. And there's something similar for morphisms, but for the sake of time, I'll skip it for now. Oh, it's not that long. I'll just write it down really quick. So here's the formula. Because I'm going to use it in a sec. So you just do the base categories monoidal structure on the components that correspond to that, and then you use the lax structure map to take care of the other parts. So I give a talk about this stuff alone, and I go into it in a lot more detail. So given a network model, let's see, F with phi mapping from S plus into monoids with times, we can think of monoids as one object categories. And now we have something which we can apply the growth and deconstruction to. So we have integral of F is a symmetric monoidal category with this sort of description. The objects are just N. So in the growth and deconstruction, you describe it as an object in the base category along with an object in the fiber that it corresponds to, but these are one object categories, and so all of them would be like N and then star, or whatever you call the one object. And so I'm just going to leave it as that. So I guess you can call it in S. Then the morphisms, are going to be pairs, a permutation, and then something G. This is going from N to N, where this is a morphism in the base category, which is symmetric groups, symmetric groupoid. So this is a permutation. And G is a morphism from that star thing that I left off, and which is just an element of the monoid. So that's going to be an F of N. So it's a graph on N nodes in our favorite example. Then the tensor of two objects is just going to be their sum, because that's what's happening at the base category level. And then the tensor of two morphisms, sigma G and let's say tau H, is going to be sigma plus tau and G, G disjoint union H, because remember that disjoint union is the thing that corresponds to the lax structure map. And so here's our symmetric monoidal category now, and just about done with the time. And so I didn't get up to the operad, but maybe it's very common knowledge that you can take symmetric monoidal categories and turn them into operads in a simple way. But this is most of the structure anyway, so I'll stop here.
Thank you very much, Joe. This is a very nice talk. Does anyone have any questions?
I have one question that is related with the work of John Baez, because in the example when you take Petri nets, John Baez talk about a logistic equation that say how this evolve in time, how this this operate network structure can be extended to these logistics equations? Yeah.
I haven't. That's a really interesting question. I haven't thought about that at all. Yeah, because the way that that stuff comes about is from open Petri nets, right? Where you have like a Petri net, just draw a very simple one, and you have these input and output data. And I just went over it really quick. I didn't even draw any pictures of this, but the way that a network model version of a Petri net would look like is, yes, here's a Petri net, is that that they're not open, and you have like these different closed Petri nets, and then you could take their overlay and give you some other Petri net. So like it's just approaching it from, like it's still a compositional type of structure, but it just looks very different at this level. So I'm not sure if there's any direct relationship, or I haven't thought about it at all.
Yeah, but it could be very interesting. Yeah,
yeah, it could be.
Okay. Yeah.
There's like a relationship between like Brendan Fong's framework for describing open things in general, and between network models. There's a relationship there already that I could describe at some other time. So there's like a connection between the two frameworks that are set up here, and Petri nets do like exist in both frameworks, but yeah, so I'm not sure. It is definitely an interesting question.
Okay, thank you.
Yeah, I think Edith might have a question.
Yes, well, more than a question is that I try to notice some things, but I passed one important thing is when you are, all these network models are given in the setting of simple graphs, yes?
Yeah, I use simple graphs as like the motivation, because they're very simple to think about, but you can do a lot of.
And yeah, perfect. And the last, I would like to see the last previous two slides, because I passed when you were defining this gamma m and given the example of these triangles where you were constructing the model, and this gamma m, I passed what was, and I was my request to ask you this gamma m is SG. I passed it, sorry. That was my question. I wanted to see what was at the end this gamma m that you obtained from the union of these two things. Okay.
Yeah, so this is
that is the gamma m. Okay. Yeah, because I was interested in that and I passed it. It's gamma b in this case.
Yeah.
Okay. Yeah. Well, thank you very much. It was a nice talk.
So there's a question in the YouTube channel. So there's Adrian Vasquez, so asking if there's lecture notes for this talk.
So I wrote up notes for myself, and I was planning to, it would only take a little bit of work to make them nice enough to make public. So I could do that.
Okay.
They're not available at this moment.
Okay. Well, I suppose I do have a question myself. So here you use the monoidal growth and deconstruction, which we briefly talked about in our emails. So So yeah, the idea is to use the Cartesian structure and categories and take it. But so is there a way of, so suppose you have a functor to categories. So you have your, well, I don't, yeah, I'm not sure if it's a good question. So you have your monoidal category. You have a functor to categories, but so instead of taking categories, you take monoidal categories, monoidal functors. And then you can take the monoidal, the Grothendieck integral of that. And that is a monoidal category, isn't it?
Yeah, so you're saying, so you could do it with just see an ordinary category and then take a map into monoidal categories.
Yeah, right.
Yeah, so there's like, so there are two different monoidal versions of the growth and deconstruction. One is where you take ordinary functors from an ordinary category to monoidal category. So this is like monoidal fibers. And then there's a different one where you have a monoidal functor from a monoidal category into cat, and into cat with its Cartesian structure. And they both give you a, so actually the, here it actually gives you a fibration which has monoidal fibers. So it's like nothing surprising because, so monoidal fibers, because all I said was that the fibers were monoidal in this setting. And then over here you get, this is a monoidal category. And this was already a monoidal category, and this fibration is a monoidal functor. And so these are two completely different setups. But if, so I was doing the covariant version. So if C is co-Cartesian, these are equivalent. These are, sorry, my writing got really bad all of a sudden. These are equivalent. So that's like one of the main results for our things. These are equivalent. And in the contravariant version, the condition is that if they're Cartesian, the base is Cartesian, then these are equivalent. And so that actually allows you to transfer the fiber monoidal structures into a monoidal structure in the total category. So here you only have monoidal structure on the fibers, and then through this equivalence, in the case of Cartesian or co-Cartesian, then it transfers into a monoidal structure on the fibers.
Okay. How essential is the co-Cartesian structure in doing this?
It's pretty important.
Okay.
Yeah. I don't want to like go as far as saying it's like completely impossible without it, but it's definitely a huge part of it. Mm-hmm.
Okay. Yeah, thank you very much.
Yeah.
Yeah, there doesn't seem to be more questions.
There is a question from Ivan.
Ah, okay.
Ivan.
So where is this question?
Ivan, you're there?
Hello, can you hear me?
Yeah.
Yeah, I was concerned about the applications. You mentioned some applications at the beginning, something like natural disasters or accidents or so. I would like to know a little more about it. If you can mention a little bit. Thank you.
Yeah. So there's a part that I didn't get to, spent too long building up to the definition, I think. But you can start to, after you get to the operad, you can start talking about algebras for these operads. And so in particular, one example of an algebra that you could have for one of these operads is that you could have range limited networks. So as an algebra, and I could describe it more if I had more time, but the basic setup is that the simple graphs operad, which I guess I'll just put an O here and say the operad that corresponds to the simple graphs network model can act on this algebra where the type of this is going to be some set of nodes that are embedded, so things that look like you have a metric space, and then you have these nodes embedded in here, and they have some kind of simple graph structure on them. And then, so things like that. And this is an algebra for this operad where you can take a network and try to, you can take like a simple graph, like maybe I'll just say this simple graph, and try to overlay it on top of this. But you could also say range limited, meaning like there's a distance which is too long to exist in our setting. So that's why I made this a metric space, and I say any two nodes that are above, 100 kilometers away from each other, you're not allowed to connect them. And so in this case, maybe these two nodes are 100 kilometers away from each other. And so when I attempt to add this, this one gets added, a problem, but this one does not. And that's so that captures this like limitation of range. I think that's probably the easiest one for me to describe at this moment. But you can do a lot of things that are like very similar, where you have like restrictions on what is allowed and what is not allowed, and these form algebras for the operad where things are sort of just always allowed, but you have like specific types coming from this like description of the networks.
Okay, thank you.
Yeah.
And just a quick question, yeah. What was the reason behind that you need to do this grothendieck construction?
So this is how we get the symmetric monoidal category that we then take the underlying operad of. So I never got to describe the how to take the underlying operad of a symmetric monoidal category, but if you already know what an operad is, then you probably already know about this construction. And if you don't, then maybe stopping at symmetric monoidal category was fine. But this is how I'm putting together all the data that's sort of disjointed in the within the definition of network models. You have like a bunch of separated pieces of data, all these separate monoids and their actions. And when you take the grothendieck construction, it just like repackages all of that data into one category, one symmetric monoidal category.
Okay. Yeah, thank you.
Mm-hmm.
Yeah, I think that I don't see any more questions. So, yeah, thank you very much, Joe, for this really nice talk. It's just, yeah, very nice. Thank you.
Yeah, thank you very much.
Yeah, thank you.
Yeah, I think we can close the session. Well, if you at some point have the notes for the talk available, just yeah, please let us know so we can read them and pass them on.
Thank you.
Okay. Well, see you next in the next seminar talk.